Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I'd like to introduce our speaker this morning. His name is Kaushik Datta. He comes to us from UC Berkeley, where he's currently a student, and he is studying under Kathy Ellick and somewhat Jim Demmel as well. He's part of the Bebop group there. And today we invited him here to talk about his work, and he's going to be talking about stencil computation and auto-tuning on multi-core architectures. So here's Kaushik.
Thank you, Mary Beth. Right, I think she summarized my basic outline. So I'll go ahead and start. So the motivation behind this talk is, first of all, dealing with the multi-core revolution, which I'm sure all of you know very well. And what we've seen when we try to run any type of code on multi-core is if you give the compiler, your best optimization flags, you still get poor performance. And if you wanted to do something like hand tuning, well, that only applies to one specific architecture with one set of core counts. So what we'd like is a broader solution to deal with poor performance on multi-core. So this is a small outline of my talk. I'm going to start with what stencil codes actually are. I'll be talking about some of the cache-based architectures that we run on, followed by a description of auto-tuning, at least the way that we've implemented it. We'll show the results from auto-tuning on stencil codes. And finally, we'll talk about machine learning as another way of dealing with some of the issues that occur when we auto-tune. So briefly speaking, stencil codes are what I've been working on so far. And what they are they result from finite difference operations that occur in partial differential equations. And you see stencil codes in a lot of different places. But in essence, what they are nearest neighbor computations. So in this case, I represent a regular grid here, a 256 cubed grid. And for every point in this grid, we want to do a nearest neighbor computation. So we've chosen this very simple 3D 7-point stencil with constant coefficients. So for every point in this grid, we're going to be doing a nearest neighbor computation with that point as well as its two nearest neighbors in each of the 3 dimensions. So in this case, we're doing 8 floating point operations per point. And I'll talk a little bit more about this in a second. So where do stencils fall in with other mathematical computations? One way to classify it is arithmetic intensity, which is the ratio of flops to DRAM bytes transferred. And in this case, we're talking specifically about compulsory misses. We're not going to deal with other types of cache misses that may occur because hopefully we can find out ways to avoid them. So if we look at the spectrum of arithmetic intensity, you could see that dgem, for instance, a double generalized matrix multiply, is O of n because you do n cubed flops and you transfer n squared data or thereabouts. So this pushes towards the computation side of things, towards being compute bound. FFTs are log n, so they could be either computation or bandwidth bound or memory bound. And in our case, we actually have constant arithmetic intensity. And that's the case for both stencils as well as sparse matrix spectrum multiply, as well as a lot of other kernels. And this is going towards the memory side of things. So stencils, at least the 7-point stencil, we're only doing 8 flops per point. We expect to be bandwidth bound rather than compute bound. So the first thing we did is we wrote a reference stencil code. And you could imagine this to be naive code, but it's threaded so that you could run it on lots of cores. So it's very simple. We're doing the 7-point stencil, which is just a triply nested loop. And we've written it with p threads. So we partition it in the least unit stride dimension, and we let each one of the threads work on its subset of the grid. And the other thing I want to point out here is that we're going to run this on different multi-core architectures. So what we did in terms of thread affinity is first do multi-threading. So if you have several hardware threads available on a given core, we populate all the threads on a core, and then we populate all the cores on a given socket, and then we populate all the sockets. So that's important to know that we're not using multiple sockets bandwidth without populating each socket fully first. So I'll talk briefly about some of the cache-based architectures that we actually ran on. So here we have 3 architectures: the Intel Nehalem, Gainestown is the system name, the AMD Barcelona, and the Sun Niagara 2, which is Victoria Falls. Some of the basic features of these architectures: the Nehalem and the Barcelona are both x86 superscalar, while but the Nehalem, in addition, is also chip multi-threaded, meaning that it supports 2 hardware threads per core, as opposed to the Barcelona, which only has 1. And the Niagara 2 is chip multi-threaded, but it's not x86. Now, if we look at the socket, core, and thread counts, they vary pretty drastically between these 3 architectures. So the Barcelona, well, first of all 3 are dual socket, and that was done to provide fairness. But the Barcelona has 4 cores per socket and a single thread per core, so it's 8-way parallelism, while the Nehalem has 4 cores again, but 2 threads per core, so it's 16-way parallelism. And the Niagara 2 has 8 cores per socket and 8 threads per core, so it's actually 128-way parallelism. So we have to deal with this issue of having drastically different numbers of hardware threads available and still get good performance across all these architectures. And as I've said before, we expect the stencil computation, or at least the 7-point stencil, to be bandwidth bound. So one important thing that we can do is try to set an upper bound on our performance by using stream copy, which is very simple. It's just something that you can download off the web, and it's just copying from one array to another, and it's written in OpenMP, so lots of cores can run it. So we ran that benchmark on all 3 of these platforms, and what we saw is that the Nehalem did the best, getting almost 34 gigabytes per second. The Barcelona got 15, and the Niagara 2 also got 15. So we're going to translate this into an upper bound on stencil performance in just 1 second. So right now, we took that reference implementation and we ran it on all 3 of these platforms, and we plotted the performance as a function of the number of cores we use. So the Nehalem and the Barcelona both have 8 cores, and the Sun Niagara 2 has 16 cores. And just to note, when you go to the last set of core counts, that's when you actually go off socket. So going from 4 to 8 here means that you're using your second socket, and similarly here, and similarly with 16 cores here. And what we've seen is that this is the performance that we're actually getting with the reference implementation, and the red line is what we expect to get using stream. So if we were able to achieve stream bandwidth and we only had compulsory misses with the stencil code, this red line should be what we expect to see in our performance. And what you see here is that we're nowhere near the red line in any of these 3 architectures. But moreover, we don't even see any type of parallel scaling. So you could see here that for the Nehalem, the best performance we're getting is with 4 cores, which is not what you would want if you have more cores available. So there's obviously some major issues that need to be addressed, and we'll talk about them as we go through this talk. Right, and this is actually quantifying what we see. So the best performance on all 3 of these architectures ranges from 17% of stream predicted to 26%.
Does the stream prediction also vary based on the number of cores?
That's a good point. We only ran the stream using all threads on all cores. So we would not expect 1 core to reach this line. We only expect the full concurrency to reach that line. We didn't run stream for less than all the cores and all the threads. So.
It's possible that they also peak at like 4 instead of
For stream. Possibly, but that's a little discouraging. The other thing about stream is that it's not optimized. We're going to go through and systematically optimize our stencil code. The stream benchmark is just a very simple OpenMP implementation that we may be able to surpass. So one of the issues that we see is the cache capacity per thread. So for the naive stencil code, our working set size, which is some detail that I won't go into right now, is more than 2 megabytes per thread. I mean, that's how much you need to avoid any type of capacity misses. And what we see here is that the Barcelona only has 1 megabyte per thread, and the Niagara 2 has 64 kilobytes per thread. So obviously, unless we do some blocking, we're not going to get good performance. And we saw that with the original the reference code that I just showed. The Nehalem has 2.3 megabytes per thread, so it actually has a chance of doing well by avoiding these capacity misses. The larger issue here is some compiler deficiencies. So one of the reasons compilers may not do well is listed right here. So what we show here are compiler transformations from easy to difficult. And these last two, data structure transformations, algorithmic transformations, these are domain-specific transformations. And a lot of times, general compilers won't be able to do them because they don't know that they can do them. But even some of these earlier, easier transformations, a lot of times the compiler doesn't know how to do properly. And in our case, for the 7-point stencil, we're not even worrying about these transformations because we don't need them. The earlier transformations, doing things like tiling or simdization or loop unrolling, a lot of times the compiler will try to do them, but they use simple heuristics. And those heuristics may not be accurate across a range of architectures. So that goes to the second point, the fact that a lot of times or I actually won't get into autotuners yet, compilers will use simple heuristics that may not be accurate for every platform that they're running on. So they're not actually running the experiment. That's the problem. So now I'm going to start talking about auto-tuning. And generally, auto-tuning became popular because you could do some domain-specific transformations. You could imagine this as being almost a domain-specific compiler in some ways. It often runs the experiment instead of just using simple heuristics. And we want performance portability. The multi-core revolution not only has produced lots of cores on a die, but it also produced a huge variety of architectures with differing core counts. So we have to be able to handle that. And when new architectures come out, we still want to be able to use code that we've already written once to run well on those architectures. So that's the point of the second bullet, that we want something that's portable, that's scalable, and that's effective. Auto-tuning can also be used for several different metrics of merit. So like performance is probably the primary one, but you may want to worry about power efficiency, for instance, and you can always tune for that instead. And we want to be able to minimize programmer effort. And I'll go into this in more detail later, but hopefully it's something that you can write once for a given architecture and run well across a variety. So that productivity is there. Right, and we're letting the machine figure out how best to do this. There have been some success stories with auto-tuning in the past, FFTW, Spiral, Atlas, ASCII, but most of these are serial. Some of these are coming up to become multi-core, but we'll show our parallel implementation shortly. So the auto-tuning steps that I've sort of outlined and I think are relatively general is first we want to identify motif-specific optimizations. I should have defined motif earlier. Motif is just a simple a way of doing computation and communication. So you can imagine stencils as being one motif, dense linear algebra as another, sparse linear algebra, structured grids. I mean, these are all different types of computations, and there's always subsets within them, but in our case, we're dealing with structured grids and Stencil specifically. So we're coming up with domain-specific transformations that are specific to stencils. Then we want to generate the code variants based off of these optimizations. And I won't go into too much detail about that here, but for our case, we wrote a lot of Perl scripts. and that's something that we can make smarter and that we're working on making smarter, but it's not something that I'm going to address specifically in this talk. And finally, from these optimizations, you generate this huge parameter space, and you want to be able to efficiently search through it to find an optimal configuration or near optimal configuration. And I'll be talking about that more later. So right, first we're going to identify the motif-specific optimizations. So how do we do that? Well, we saw the performance that we got before, and these are some of the problems that may be occurring that's hindering our performance. So for each of these problems, we set up an optimization for it. And we'll go into each of these in more detail as we apply them. So in terms of traversing the parameter space exposed by these optimizations, we produced this huge parameter space. What we did to make this problem a little bit more tractable is as we applied each optimization, we fixed that value and used that for the next optimization. So in this case, if we have three optimizations, for optimization 1, we found the best value, we fixed it. We went to optimization 2, found the best value, fixed it, and so on. So this is a pretty good solution right here. We're not saying it's the best one because obviously we haven't explored the entire space, but it changes an n to the d problem to an n times d problem. So it just makes the search a lot faster and tractable. So now we're actually going to talk about stencil auto-tuning. And this was work done by me and a couple of other people that was presented at Supercomputing 2008. So again, this is the reference implementation, and this is what we saw. So the first optimization we did is we took these architectures, and here we've highlighted the DIMMs on all of 3 architectures. And you can see that all 3 of these are NUMA machines, non-uniform memory access. So the problem here is that if you have a single thread on one machine initialize all your data, then all of the memory pages will get mapped to that socket's memory. And that becomes a problem if the other core needs to retrieve it. So you can imagine this case where the memory that you need is on this socket's memory, and the core is over here. So it actually has to go through hypertransport or quick path for Intel. And that's actually a very expensive operation. So what we did is we utilized the first touch policy to have the cores and the sockets, the memory pages that the cores need, mapped to the same socket. And what that did is when you go off socket, which is right here and right here, it gives us a major win because now you don't have to do as much inter-socket communication. The next thing we did is array padding, and this was to address the problem of conflict misses. So we're changing the data layout so that we can get better behavior from our code. So this padding was tuned over. We had something from 0 to 31 doubles, and we just searched over it, found the best value, and set it for each architecture. And that actually helped a lot on the Victoria Falls machine because that has small, low associativity caches. So data placement really does matter. But it didn't help as much on the Nehalem and the Barcelona. The next thing we did was problem decomposition. And this addresses both parallelization as well as cache locality. So I won't go into all the details, but basically, right here, this is a chunk that gets allocated to a single core. And we've broken that chunk up into core blocks. And that changes to traversal through the chunk so that you get better cache locality. Each of these core blocks can get further broken down into thread blocks. And this is the case where you have more than a single hardware thread per core. So for the Niagara 2, for instance, you have 8 hardware threads per core. And you want to you want to effectively utilize the small caches for the cores. So you can group the threads together to make sure that they do that. And finally, we did register blocking. And all this is loop enrolling in different dimensions to utilize your registers as effectively as possible. So this is this doesn't actually change the actual data structures you're working with. This basically changes the parallelization as well as the cache blocking and the loop enrolling. So if we do core blocking, we see that this is a universally successful optimization because all three architectures do better. And this is a function of what I showed earlier, the amount of cache that you have available per thread. By blocking the problem, you don't have to worry about that anymore. You're making sure that you get good cache locality. And then if we do register blocking, this doesn't help as much, but this is mainly due to the fact that this is still a bandwidth limited problem. So you don't expect to see much of a benefit from effectively utilizing your registers at this point. The next thing we did was software prefetch. This was basically to hide some of the memory latency, and this wasn't that useful, but it may be the case that this optimization helps later optimizations. I'm not sure about that.
Yeah, to some extent, the same comment applies. Your bandwidth bound prefetching can't tolerate latency if the bandwidth is completely saturated already, right?
Well, software prefetching can sometimes help your effective bandwidth because you're reducing your latency a little bit, if that makes sense.
Well, you're throwing concurrency at the problem, but if the bandwidth is bound, then
I agree. I mean, you're still bandwidth bound. We didn't expect it to help that much, but we thought, it's worth a shot and see if it actually helps. Okay, so then the next optimization. Oh, I'm sorry. Someone else have a question?
Yeah. What else did you use on the x86s?
These are Linux-based machines.
All of them?
Yeah, I think. Yeah, all three of them are Linux-based.
I'm not that familiar with Linux. They have a convenient interface to specify where you want your memory placed in terms of NUMA architecture.
What we did is we used the first touch policy. So every thread initialized the data that it would be operating on. So if a thread is on a given socket, the memory page will get mapped to that socket's memory so that you don't have to worry about inter-socket communication.
So that's a policy that you specify?
No, that's a policy that is typically implemented on most machines. So if you do that, if you have a NUMA architecture and you let each thread initialize its own data, the data that it'll be working on later, it'll properly get mapped most of the time. So. Yeah. Yeah, it's actually a Linux policy, right?
So the reference differs in that it simply doesn't, it initializes the data eagerly from some main thread.
Oh, you mean initially what we were doing?
Yeah.
Right, initially we had just thread 0 initialize all the data. And that means that everything got mapped to that single socket's memory. And so the second socket had to do inter-socket communication to get the data that it needed. So, yeah. But that's a good question. Okay, so now that we've done this, at this point, this is all still portable code. And it's the same code across all three architectures. But that may not be the best thing to do. At this point, we started specializing. So the first thing we did was SIMDization, single instruction, multiple data. And this is no longer portable. This is only applicable to the x86 machines. And we don't see, so this is a completely different code base where we use different intrinsics to implement. And in this case, we don't see much of a benefit from SIMDization because we're still bandwidth bound. And this is really addressing more compute type kernels. But what the SIMDization allowed us to do was there's a separate intrinsic once you've SIMDized for doing cache bypass. So in our case, we have DRAM and we have two separate arrays, the array that you're reading from and the array that you're writing to. And for every point, you have 8 bytes that are going to be read for a double. And for the write array, right now what we're doing is we're reading in the double as well as writing it back. But this traffic right here is actually superfluous. So we can actually get rid of that by using the proper cache bypass intrinsic. And that reduces our memory traffic from 24 bytes per point to 16 bytes per point, which is huge. You're reducing it by a third, so you should see a commensurate increase in performance. And we do. So the cache bypass instruction here is shown as in pink. And you can see here that it does extremely well for both of the x86 architectures. So that was actually very valuable. And for the Victoria Falls machine, what we did is thread blocking. And this is still portable code, but it's specifically designed for the Niagara 2 because we have we have 8 threads per core, and they're all using the same small low associativity cache. So what we decided to do was have 8 threads working in conjunction on the same parts of the data at once instead of being spread out. And because we get better cache behavior, we also see slightly better performance right here. And so that's one sweep through all our optimizations, what we've done so far. At this point, we can ask ourselves, if we did a second sweep through this data and doing most of these optimizations again, how much better can we do? So we did a second sweep through all of these optimizations, starting with the best configuration here. And the second sweep didn't really help us much. It helped us a little bit on the Niagara 2, but I mean that kind of shows that, okay, we're getting pretty close to what we can reasonably hope to do on these architectures. So where does that leave us? Well, the full tuning now, we get 95% or 96% on the x86 machines of what Stream predicted. And then on the Niagara 2, we actually get 122%. And that's due to the fact that the Stream wasn't optimized, as I mentioned earlier. So this is actually what we hope to see. And in terms of how much better we're doing over the reference implementation, well, we're at least doing 4.7x better and up to almost 6x better over the reference implementation. And we also see parallel scaling. So over the single core performance, we see 4.5x improvement going from 1 core up to 8 cores on the x86 machines. And we see an 8.6x improvement going from 1 core up to 16 cores on the Niagara 2. So if you remember the original reference implementation, which is just the purple bars shown here, it didn't show any type of scaling at all. And now we actually start to see scaling. So it's actually very positive. And this is for a bandwidth limited kernel, which is probably a little bit harder to tune. So here are some summary graphs of what we've done so far. And this also includes optimized code for both the cell processor as well as the NVIDIA GTX280. And so these are local store-based architectures. And I'll go through everything that's shown here. So on the left over here, we have the 3 architectures we were just looking at. On the right, the green is the cell, and that's a dual socket system. The NVIDIA GTX280, which is a GPU, that's single socket. And it's the GTX280 is also the purple, but now we're including the transfer time between CPU memory and GPU memory over the PCI Express bus. And so, it's the actual performance that you'll achieve depends on, how many times you have to transfer for your given application. But we show both the optimistic upper bound as well as the pessimistic lower bound so that, we're more even-handed in our presentation. So what you see here is that the 3 cache-based architectures do, at best, as well as the cell. And the GPU does significantly better if you're not transferring between the 2 memories. If you are, it actually does the worst by far. And the reason the local store-based machines actually do so well is because you have explicit data movement over your data. So you can optimize for that a little bit better. And you also have some higher bandwidths on some of these machines. So for the cell, you have direct memory access operations that help you control data movement, which makes things more efficient. And then for the GTX280, you have a special type of memory which is achieves very high bandwidth. And then we also looked at, well, actually, the other thing I should mention here is that the trade-off here with the local store-based architectures is the lack of portability, because you have to write the cell with DMA operations. For the GPU, you have to write in CUDA, which is a whole different programming model completely. And so it's a question of whether you want to trade off. If you want to put in the time to write for a different programming model, you can achieve much better performance. We also looked at the power efficiency, and we basically hooked up a digital power meter to each of these systems to figure out how much power draw does it have. And what we saw is that the local store-based machines actually do much better. And again, they have you're explicitly controlling the data movement, which helps save some power. Yeah.
Did you also do the stream benchmark on those local store machines, or at least two of them? What I'm wondering is how close to memory bandwidth
are they achieving?
Saturation were you able to get?
I have some backup slides that might be able to address that problem.
I imagine it would do okay. There's enough MLP provided by those GPUs to probably drive the memory bandwidth fully. But
right.
I think it's really interesting that you were able to do as well as you did on the x86, actually.
Oh, okay. Well, that's encouraging.
I mean,
so
it is an issue. I mean, especially with Gainstown, with all the bandwidth it has, and the configuration you used, it's interesting that you're still able to drive it up to near stream with this very data-intensive stencil.
Yeah, and we really optimized it. So this is just a backup slide of the full tuning done on the cell and the GTX280. We don't. Yeah, we didn't. I guess we did not actually run stream on these machines. I wish we had, but.
120 gigabytes a second.
Oh, actually, you know what? I do have some. Hold on. Here we go. So this is the stream bandwidth achieved for both of these architectures. So these numbers, the cell 37 gigabytes is in line with the Nehalem, but the NVIDIA 128 is just off the charts. And that's because it's using a special memory that has less capacity but much higher bandwidth.
Every value 6 times, so you'd have to do the math, right?
Yeah.
127 gigabytes a second is, call it 128, so that's 16 8-byte values.
Right.
If you use everything 6 times, then 16 times 6, so it's almost 100 gigaflops, it sounds like.
Yeah, I think that's right. So, right, I'll go back to where I was.
I have a comment about the cache bypass too.
Yeah.
I mean, it isn't so bad if, when you allocate and have to fetch the thing, if you get the whole cache line written before it's written back. And so, in some sense, how the Stencil's architected is competing with that optimization, right? If I write a partial cache line, then the lack of cache bypass hurts me.
Right.
A lot. But if I write a full cache line per thread block, say,
right, then
it's not so bad. So it's an interesting interaction between those.
Yeah, exactly. So, I mean, the Stencil kernel is kind of an optimistic case where you're writing every point in your cache line, and so you save a lot of memory traffic by not having to bring that cache line into your cache. Right. Okay. So So the last part of my talk is actually going to address machine learning and auto-tuning. And this was a workshop paper done with me and a couple of other people that was presented at Hot Par 2009. That was in Berkeley. So the motivation here is that the configuration space that we've been dealing with is huge. It's over 40 million different configurations for a simple Stencil kernel. And this problem of dealing with a huge parameter space will only grow worse as more cores are added to a die and as you start looking at more complicated applications with several different types of kernels and more parameters that need to possibly be tuned. So our previous method of doing this expert optimize where we fixed each value as we went only takes you so far, and it requires a lot of extra expert knowledge to be able to do, to be able to order the optimizations in a certain way and then to traverse it. What we'd like to do right now is address the problem of trying to tune these kernels for non-experts, for people who may not know as much about either the kernel or the architecture. So the machine learning approach is kind of promising. It's meant to efficiently traverse this auto-tuning search space and find a high-quality solution quickly. And probably the most important part of it is the fact that it requires little domain knowledge. And I'll talk a little bit more about that. As the problem gets worse, hopefully machine learning can step up and be able to deal with these larger spaces. So the two platforms that we looked at were the AMD Barcelona that we already discussed, as well as the Intel Clovertown, which is a slightly older architecture with a front-side bus. These are both x86, 2 sockets, 4 cores per socket, single hardware thread per core. And we used 2 separate compilers on them, GCC for Barcelona, ICC for Clovertown. The one thing that we should note here is that we actually started collecting performance counter data here. So we used PAPI to collect information about things like cache misses, TLB misses, running time. Well, running time was a separate timer, but we are collecting more than just timing data. So what we did, well, actually our goal is to find the best configuration. So what we did is we sampled 1,500 random data points within this huge configuration space. We ran the stencil and found the performance that they result in. And then we had to try to identify the relationship between the configuration and the performance and manipulate it so that we can extract useful, actionable items from. So this is what the algorithm is doing. The algorithm is called KCCA, but it's based off of CCA, which is Canonical Correlation Analysis. And this slide sort of describes what CCA is doing. So on the left, we have the configuration space, and I'll talk about that in a second. And on the right, we actually have the performance that you're seeing. And this is the raw data up here. And you can imagine the purple points correspond to each other. So this purple point may correspond to this performance. And what CCA is doing is projecting onto dimensions of maximum correlation so that once you transform into this projected space, you should cluster similar performing points together. So the performance features are clustered here, and the configuration features are clustered here. So there's a couple of challenges that we'll deal with as we use the machine learning methodology, and I'll go through them quickly. The first is how to represent configuration parameters and performance metrics as feature vectors. So right here, this is the set of optimizations that we actually used in our auto-tuning methodology that I was showing previously. And this is the parameter range for these different optimizations. And what we did, well, this is the number of configurations for each of these separately. So you can multiply them to get the total number, which is approximately 40 million. The feature vector basically just takes them and groups them into a feature vector like this. And the same is done with the performance metric. So again, here we're collecting performance counter data. And we also use the power meter to measure watts. And our feature vector for the performance metrics similarly gets mapped into a vector like this. So these are the two vectors that we'll be dealing with. So now we'd like to be able to compare vectors. So how do you compare two configuration vectors or two performance vectors, and what type of metric do you use? So right here we have 3 different configuration vectors, and how do we measure the distance between them? Are x1 and x2 more similar than x2 and x3? So the problem here, or part of the problem, is that some of this data is now numeric. So what we did is we converted that into numeric data, and like plain and pencil just get mapped to integers. And then we used the Gaussian kernel to compare different different thread counts, for instance, or different prefetch types. And this is standard machine learning methodology. And that produced an actual number that we can use to compare the distance between any two vectors. So at this point, we can generate these two matrices of pairwise comparisons between the vectors in each space. So for the performance vectors, we can do a pairwise comparison to figure out what's the difference between any two vectors, and same with the configuration vectors. And how do we leverage this to actually use machine learning? Well, what we did is we have these matrices. The KCCA algorithm is actually an eigenvalue problem. And we take this kx and this ky, and we set up this problem, and we solve for the eigenvalue and the eigenvectors associated with it. And so this is part of the model building that is involved in this process. And what that does is by doing this, we're able to cluster similar performing points and similar configurations together to find the maximal correlation between the two. So how do we use that to actually come up with new points that may also perform well? So in our hold on just for a second. OK. So right here, this point, you could imagine, is the best performing point out of our 1,500 data points. So this is in the raw space. We transform that and bring it into the KCCA data space. And so in this space, the nearest neighbors will also be good performing points. So we can look at the nearest neighbors, and we transform that back into our configuration space to find out which configurations these resulted from, and map it back to our raw data space. And now they could be all over the place. You could see that these are spread out all throughout the space. So those are all part of our original training data set. And we still haven't generated any new points based off of this data. So at this point, what we can do is we can use a genetic algorithm to permute features from the configuration feature space to try to generate new points that also have a high likelihood of performing well. And that's basically what we did. So we generated the new points, and we ran them to figure out what their performance would be. So let's see how this algorithm actually performed. Right here, we have a couple of benchmarks that we use to compare against the machine learning. The first is NUMA Optimization, which I've shown before. The second is the expert optimize, which I've also discussed before, where we simply fix each value as we go. And to address the problem of, is KCCA actually working? Is it doing better than what, if you randomly selected a point in this 1,500 point data set, would that be better than what KCCA is actually generating? To disprove that notion, we also have 2 more benchmarks. The first being random raw data. So out of our 1,500 points, we choose the best one, and we'll present that performance. And then genetic on raw data. So we take the top 3 performing points, and we permute some of their features to see, if you randomly chose or if you took the random data set and you chose the best 3, permuted their features, would that result in better performance than what KCCA did?
So you're doing this comparison within bounded compute budget or something like that to make sure that it's a fair comparison?
Oh, you mean in terms of the amount of time took, it's the training data took and we'll talk about that, yeah. Okay, so first I'll just show the results and I'll talk about the training time that it involved. So in this case, for Barcelona and Clovertown, we both looked at both the 7-point stencil as well as the 3D 27-point stencil, which I actually didn't discuss, but it's just more flops per point. And the gigaflop rate is on the y-axis. So right here, there's a lot of data, and I just want to clarify. This is no optimization. This is where the expert optimized, which is what I showed previously in this talk. This is the random, so you take the best performing point out of your random points that you've chosen. This is the genetic on random, where you combine different features from the best 3 performing points. And this is the machine learning. This is the KCCA algorithm. So on Barcelona, you see that the KCCA algorithm does the best, but it barely beats out what random already did. And for the 27-point stencil, it does as well as the expert optimized, but it's certainly doing better than what random would give us. So that's encouraging. And for the Clovertown, you can see that the 7-point stencil, we're just limited by the front-side bus. So no matter what you do, you're limited. You have a certain bottleneck that you really can't surpass. But for the 27-point stencil, you see that it does significantly better than any of the others. So this is still a small data set. I'm not saying that this is convincing evidence that machine learning has worked, but it is promising. And getting to your question about how much time does it take to generate your training data and to produce your model? Well, for the exhaustive search, where we had 40 million configurations, if you did that, it would take 180 days. So that is your worst case scenario, but you're guaranteed to find the optimal configuration. The expert optimized, ordering the optimizations required a lot of expert knowledge that we claim cannot really be quantified. So we leave that the way it is. But actually, applying the optimizations consecutively took about 4 minutes. I shouldn't say our technique here. The machine learning technique took 10 minutes of time to run the 1,500 data points. The training time to build the model to do that eigenvalue problem took about 90 minutes. And a lot of that was just run on a laptop that is doing other things. So that could possibly be sped up. And there could be better algorithms for doing the eigenvalue solve that could also speed that up. And then doing the genetic algorithm where we introduce new points, then see how well they run, that took 1.6 minutes. So the total time here is still less than 2 hours. So you can see here that the expert optimized does by far the best and exhaustive does by far the worst. But what I'd like to impress on you is that the machine learning is promising. This is just going to become a worse problem as things go on, in terms of the number of cores that are available, the number of parameters that are exposed as you build larger and larger applications. This is one approach that will hopefully get better as time progresses. So some conclusions. Compiler alone, as we've shown before, did not do well at all. We saw between 17 and 26% of stream predicted performance and no parallel scaling. The best performance was not even at the maximum concurrency. Auto-tuning was really valuable in trying to get good performance on these systems. And I mean, the reason we have parallel systems, is for performance. And if you're not getting it, then you're wasting resources. So, auto-tuning helped, utilize the full resources of the system. And it was also productive in terms of the same code was used for the most part across all 3 architectures until we started getting into some ISA-specific transformations. And the machine learning provides good results, but training time is still an issue. So, it's a promising approach, and it's something that we're going to continue to look into. But we're betting that that helps as time progresses. So finally, two applications of this work. At LBL, the Lawrence Berkeley Laboratory, they're using Stencil auto-tuning as a building block for a green flash supercomputer. And basically, the green flash is building a very highly customized supercomputer that can do kilometer resolution climate models, which is very difficult to do because the supercomputers now are built generally to run lots of different codes, and it's just it would eat up too much power to build a large enough supercomputer to do kilometer resolution climate models. So they're actually building very specialized hardware and co-tuning it with software using auto-tuning to get as good performance as possible without drawing a ton of power. So it's very interesting research, and it may be worth looking into. And in Germany, Dr. Franz Josef Freund is using Stencil tuning based off of a paper that we presented to do oil exploration. So, and to get better performance from this oil exploration code on a supercomputer center that is located in Germany. So that's basically it. You can always email me if you have questions. And I listed my website here, which has the full publications that this work was drawn from. So any questions? Yeah.
So I just want to clarify for the memory initialization, so and also the write out because it's related to the cache paths, right? So you have one main thread, so allocate a big chunk of the data, right?
It's initializing the data, right?
Okay, initialize the big chunk of array, right?
Right.
So then you transfer the data to each of the threads, and then each of the threads use this NUMA affinity for the memory, right? Then later on, when you finish the computation, when you write out the data, do you write out the data in the same memory for each thread, or you write to the main original array?
This is before you use the NUMA optimization, or after you use the NUMA optimization?
After you do the NUMA optimization, right? Because you use the cache parsing. As I understand, there's a combine, that's called combined write, or non-terminal temporal write, right?
Right. So you have your read array and your write array. You're not bringing the cache lines from the write array into your cache. That they're still in memory, and you're just going to write straight back to them. And so that's where the bandwidth savings occurs, because you don't have to bring that in as well.
Yeah, that makes sense.
Okay.
And also another question. For the thread affinity, originally your policy is you want to use all the core on one socket, then you use another one.
Right.
What's the rationale behind this?
It's just, it makes the data analysis more rational because, a lot of times, if you use the default mapping on a given architecture, it might use one core on one socket and then use the second core on the second socket. So you're already utilizing both sockets' bandwidth, and that's not really a fair comparison. Because you're already getting both sockets' bandwidth, what you'd like to do is be able to figure out, okay, if we populate all the threads on a core and all the cores on a socket, what can we get from that socket alone without utilizing the second socket's bandwidth? And so that makes reasoning about your performance much easier because you understand that you're only getting a single socket's bandwidth at a time. So. Yeah,
but if you want to utilize the full bandwidth, right? Suppose you have like 4 sockets, you want to use 4 cores. You want for each socket,
right.
Yeah. You want
right. So I'm not saying that that's not what you should do. If you have fewer threads than you have total available, like if you have an 8-core system and you only have 4 cores, you should not use just one socket's bandwidth. You should use 2 cores on each socket But in our case, just to make the data analysis more rational and to understand exactly what was happening, this is the technique that we took.
So that's true of, I mean, that is, you might achieve better performance by using all the sockets in a data-intensive communication to whatever you would call it, algorithm. But of course, if there's an L3 cache for the socket, and it's computationally intensive, so the operating system has a real challenge. How should I map cores onto processes in such a way that, you know, the compute-intensive guys are all, you know, highly local to each other, so the caches work, and the data-intensive guys are all spread out over the. It's a very interesting problem.
Yeah, it's a tough problem to deal with. So this is the way we chose, and it felt like the most rational thing to do in terms of analyzing data, but it's certainly not what you would want to do in all situations. So. Go ahead.
Okay, there's somebody else. And for the padding, right, you also have one optimization for the padding, right?
Right.
So when you for the padding, so how do you decide what's the size you want to pad?
Oh, that's tuned. So every architecture, we tune it and we find a different value, and you know, hopefully that gives us the best data placement, so you know, we avoid any type of conflict misses. Wait, is that what your question was, or?
Yeah, I want to say how do you decide the range, right? The upper
Oh, the
bound,
range. Oh, okay. So it's a 256 cubed problem that we're dealing with. We chose the range to be anywhere from 0 doubles to 31 doubles that you can add on to one dimension of the array. And, you know, I mean, that again has some expert knowledge involved. You know, we kind of figured that within that range we would find something good, because after a certain point, you know, the memory footprint of the grid becomes too large, and that becomes a separate issue. So.
Greater than 32 depending on the problem of the architecture.
Right. I mean, that's what we chose. I mean, we're not saying it's the best, but it seemed like a rational approach. Yeah. So, go ahead.
Can you talk a little bit, or just provide some pointers into what's your thinking about auto-tuning in a kind of more generalized, let's say, software ecosystem in terms of the tool chain? Because overall, this approach is very tightly coupling the software with the hardware.
Yeah.
Many vendors don't work this way, right? They ship the software, and then their customers can operate the hardware. So, is there any thought about how to basically package these things such that you know, they don't really burn very specific information? I mean, that's the goal of the entire optimization, to really make your software tailored to one particular hardware profile. But is there maybe some thought about how to update such a profile if you, let's say, you upgrade your hardware or something like that? Or this is something that's completely out of the radar for this research?
Okay, so your question is, how would you deal with auto-tuning for different architectures, or how you could actually change?
So let's think about it from, let's say, Microsoft's perspective.
Okay.
So we give development tools to ISVs who develop libraries, who are then embedded into other software products, who are then used by end customers.
Right.
So pretty much, you know, you have to think who's going to run these optimizations and at what stage,
right?
And how they're going to get the actual right profile to the end customer.
Right.
So
Is this
something that kind of you live for us, essentially, in terms of the research?
So I hope I'm going to answer your question, and tell me if I'm not. The auto tuning that we've done, you know, it's basically what it's still dependent on what compiler you're using and how well the compiler can generate the code. But you know, we're not changing the hardware. We have, you know, a fixed set of optimizations and a fixed set of parameters that we're going to search over. And you know, given a new architecture with other core counts or a different family of processor, we can still run that same auto-tuning framework, but it's still limited by what compilers you have and how effectively they generate the code from, from your source code to the actual machine code. And that's another issue that, if you have a poor compiler, you're still going to get hosed no matter what auto-tuning framework that you have. So it's basically where you are in the software stack and what can you expose, what knobs can you tweak to get good performance. I mean, if you're at the compiler level, that's one thing. If you're at the actual source code level, that's another. And you basically do the best you can with what APIs are exposed to you at your level.
Yeah, but Yossi's question, as I take it, is when?
When do you do it?
When do you do it?
You mean
what's the deployment story?
You mean whether you do it at install time or runtime or...
Can we auto-tune that late?
Right. Okay, so the question of when...
Can I get my auto-tuning patch based on my hardware through...
I see. I understand. Okay. That really depends on what you're trying to do. In our case...
yeah, this works really well for HPC customers.
Right.
Yeah, but imagine...
Yeah.
Imagine you're an ISV. You're selling a big, big computational fluid dynamics package.
Right.
And it wants to run on everything. It wants to run on all the x86s, all the Linux systems, all the Windows systems, all that other stuff. You've got some number of versions of the code. How many versions? Do you have a version for each of the configurations that's shipping this year?
Yeah.
How does that ISV, just imagine that ISV, how does that ISV use auto-tuning to guarantee he's competitive on all platforms?
Right.
So actually, I brought this issue to Jim Demer at the Carla
at the retreat?
In January.
Yeah.
So the deployment issue of those auto-tuning technologies.
I mean, my favorite way to do it is to auto-tune it from an intermediate. So generate an intermediate and leave enough of the infrastructure around so you can essentially lower it to optimized code when you install, say.
Right.
But this is the question.
This is a difficult question. I don't know if I can give a better
answer either. Right? Jim Demmel doesn't know the answer.
We'll see in 2 weeks.
We'll see in 2 weeks. We'll see.
Maybe we'll have a solution by then. No, that's actually a very good question and something that I've thought a little bit about, but I could not give you a good answer to that. That's something that is dependent on how many architectures that you may want to deploy on, what you're actually doing. When is the earliest that you can actually put these optimizations in? I mean, and how large do you want your code base to be? So in this case. For this Stencil auto-tuner, I basically compiled a huge number of code variants all at the same time, and that just increases your overall code size, and it's really a trade-off, and it's a difficult question. I don't know if I can do it justice. So, yeah.
Somewhat related to this question, and you mentioned at the start of your talk about how you actually generate the different pieces of code, because when I talked to you in January, I got the impression that a lot of this was still, even though it was called auto-tuning, it was more the identifications of things for auto-tuning but still being done kind of more or less by hand, or is not as automated as it could be. So then is there that
the code generation part of it?
Well, I mean, all.
Oh, right. So the auto is loosely stated to be auto.
The code generation piece kind of speaks to this as like what could possibly deliver, even if.
So my assumption was that this particular set of optimizations could roughly be boiled down into a set of constants that you change, or is it more radical with code reorganization? Loop unrolling, for example.
Right. So
that's not just a constant that you push into the code. And that brings interesting questions about debugging. If I wanted to debug that code, what version do I look at? The one that was auto-tuned or the original naive one?
Right. So in our case, we don't. It's an evolution process. So originally we had the naive code, and then we hand-tuned it, and that ran well on a given architecture, but it wasn't portable. Then we wrote this code generator in Perl, which is not smart in the least. It's just tons of print lines, and it'll generate all these different variants for you. But there could be, it's right. The Perl will generate C source code, and you have all these different code variants. But in terms of correctness checking, or in terms of being able to just tell the Perl script, I want to do this optimization, it's really not that smart. So the next step is really to have a code generator where you can specify what kernel you want to run, what transformations you want to do, and hopefully what output you want to have. Do you want to generate CUDA code? Do you want to generate C code? Do you want to generate cell code? And it would be able to handle all those cases. And that's actually something we're looking into now. Not me specifically, but another person at Parlab who will be giving a talk at the retreat. He's set up this framework where you have this intermediate representation of what you're doing, and you can basically specify from this intermediate representation, I want to do this transformation, and I want to print out CUDA, for instance, and it's able to do it. And it's still very preliminary, but this is actually the direction that we want to go, because the Perl scripts are just not sustainable. It's not. This was in some ways just a proof of concept to show that, look, we're missing out on all this performance. But I kind of glossed over the fact that the code generation part of it is very difficult, and you may want to output from many different types of architectures. So it's something that we're looking into, but it's something that I probably should have spoken a little bit more about, because it's a glaring. It's the elephant in the room.
Yeah, we're a software company, software tools company.
Right.
So we have a maybe disproportionate interest in that aspect of it.
Right. So currently this intelligent code generator, not just the Perl scripts, is written in Lisp, and it actually can generate some CUDA and C. But it goes from this intermediate representation to print out for, and then takes that and prints it for a given platform or programming model, more specifically. But it is still a very difficult problem. So that's the next step that we're trying to take. So, yeah.
When you think about modeling for this, like for this is the memory intensive problem, right? So that for different architectures, pretty much very similar. But for the computer-intensive problem, the different architecture difference will be huge. Those instructions, all those things will be huge. So I think about just like modeling for different architectures, so that you don't need tuning too much. You can predict.
Right.
Yeah.
And that's a very good point. Another thing that we've been working on is this roofline model, which will sort of indicate where your bottleneck is. Are you bandwidth bound? Are you instruction bound? Are you compute bound? And what optimizations may address some of these issues? So, you can only go up to, what your bandwidth will give you, or what your computation, what your functional units will give you. But to get to those bottlenecks, it'll give you some ideas. And this was developed by Sam Williams, a colleague of mine. And it's actually very useful to figure out. Originally, where I showed what optimizations we identified to be effective for stencil codes, we did that before the roofline model came out. But that experience of trying to figure out, where are we? Are we limited by the memory? Are we limited by, something else? That process kind of generated this roofline model. And I wish I had some slides on it, but I don't right now. But you're right. At a certain point, tuning is diminishing returns, and you don't want to get to that point and still keep tuning when you're not getting anything back. So, yeah. Very good.
So you talked about the stencil code being one type of motif.
Right.
Are there, well, I don't know if I even asked this in January, but since January, or even after the time of January, what other motifs are you looking at for auto-tuning?
Oh, okay. So me specifically, I've been working on other stencil codes. So I've been looking at the 27-point stencil and trying to figure out, and that actually has a very good chance of being compute bound because you're doing 3 times as many flops for the same bandwidth. But I've also been looking, well, I won't go into what I'm looking at, but our group has also looked at tuning sparse matrix vector multiply, which Sam Williams did, and he also did LBMHD, which is a lattice method, which is just a much more complicated stencil operation, and you really have to deal with lots of streams of data at that point. We're also tuning collectives, so things like barriers, or you could imagine tree-based barriers instead of linear flat tree barriers, and some other collective operations which need to be tuned for different kernels, and I think those are the primary ones. And
someone's addressing parallel
SPMV. Yeah. So when we tuned it for parallel applications. So.
Is there a parallel ASCII?
Right. So that's a good point. So we had ASCII, which is a software written at Berkeley that does tuned sparse matrix vector multiply, and that was written serially. And at that point, that's all that was around. So that's what we had. But now that we're in the multi-core era, we've tried to tune it for parallel systems, and Sam Williams did a really good job of tuning that. He used the CSR format to represent the sparse matrix. We're trying to use his optimizations to make p-ASCII, the parallel ASCII, and there was a master student who did that, but then he left, and we're still trying to deal with this problem. This is more of a software engineering problem than a research problem in some ways, but it's still work that needs to be done because a lot of people use ASCII, and p-ASCII is the obvious successor. So.
And just how difficult it is, even if you're delivering it as source and library, getting it out there.
Right. It is still a difficult problem. So. Any other questions, or? Okay, well, thank you for your time.
Thank you.